represent us on a design challenge for NASA a couple of weeks ago, and now they're presenting again what was their project and their output. Team number 7, are you guys ready?
Yes.
Go ahead.
Thank you, Dr. Garcia. Hello, my name is Anthony Agansi. This is Ango, Min Ewan, Jack Bismuth. We're Quadraxis Engineering. As Dr. Garcia said, we were part of the TSGC NASA Design Challenge. And today we're presenting our senior design project, Human Inadvertent Loads Tester in Intravehicular Activity. So we're going to go over some background information, talk about the design process, discuss the data that we collected, and give a conclusion. So here on Earth, we have an atmosphere, we have the warmth of the sun, and we have oxygen. So generally speaking, we're safe indoors and outdoors. This means we're able to construct vehicles and structures such as this with a certain amount of leeway. So a hole in your wall or a dent in your car is a minor issue and won't really present any health risks. However, when going beyond Earth's orbit, that isn't the case. Minor damage within the space cabin could lead to total failure of the mission and potential loss of life. Now, when maneuvering in the space cabin from point A to point B, they're in microgravity conditions. So in order to move, the astronauts are constantly applying loads to the structures. They apply purposeful loads in order to, like, let's say, grab a handrail and move forward, or sometimes inadvertent and accidental loads. So let's say he's moving from point A to point B. If he accidentally slips, he might hit a wall or kick a wall in order to get his bearings. So because of all of this, engineers construct spacecrafts with a large amount of unbeneficial mass and materials. This is in order to ensure the structural integrity of the spacecraft and maximize the safety factor and the safety of the crew members within the spacecraft. This has led to the typical spacecraft to be over-engineered or considered overweight. This problem leads to our motivation for our project. We want to focus on the inadvertent and accidental movements that occur on a day-to-day basis by the astronauts while they're maneuvering about in the space cabin. So those inadvertent hits while they're floating about and those inadvertent kicks and pushes, that's what we want to focus on, because within the design process of a spacecraft, these inadvertent movements are unknown. So to combat this, they basically designed the spacecrafts to be able to withstand extreme forces that the astronauts will never actually be able to exert. So we designed an instrument that simulates these inadvertent swinging and kicking motions and measures those loads. With that process, we wanted to give a range of these unknown loads. And with that range of these unknown loads, then the engineers can construct a more structural and optimized spacecraft. So a key element of our research and design was displacement and constraints. As you see on the left image, the crew member has a large amount of distance between him and the wall, meaning he has a large potential to generate acceleration, meaning he has a large potential to generate force on the structure. As opposed to on the right side, they are more constrained, they have less distance between them and the structure, so they have less potential for impact loads on the spacecraft. So this displacement is a key element in our research and design. We know that the human body can generate many different motions. However, we wanted to focus on the arm swinging motion and leg kicking motion, specifically in the X and Y plane. So we've done human experiments, we've done trial and error with different instruments, and we eventually created our own instrument. So Anne will talk about this design process.
Thank you, Anthony. So we did the human subject test, which is mimic motion, to simulate the movement of the astronaut in the spacecraft. And you can see one of our members were hanging on the sling to replicate the zero gravity. For the arm motion, we attach the accelerometer into the wrist and do the full arm swing down. For the leg motion, we attach the accelerometer into the ankle and do the knee extension. For the data of the extension that we collect is more critical than the flexion, which means the extension motion produce more forces than the flexion. The first thought, so after all the study, the first thought of the project would use the jumpy impact test to generate the forces. But the downside of this test is restricted angle and only have single member. So we come up with a better solution that we're gonna build our own instrument that have two members that represent the lower arm and upper arm. But the first one have the con is static base, which is the arm, the body cannot moving toward the wall. However, the final design can solve all the problems. We have two members that represent the lower arm and upper arm or the leg. The base is represent the human body. The sliding mechanism, how the body's moving forward. This is the wall structure and also the stopper to adjust the displacement. There are two accelerometers attached to the lower arm and upper arm, as you can see in the right image right here. We did different tests and were able to calculate and generate the data. With the instrument, we did a test that the body standing still, only the arm is swinging down, and another test is the body and the arm swinging, the body is moving forward and the arm is swinging at the same time. And I'm gonna give you more detail about the data that we collected.
Right, thank you, Ann. So this is the raw data that we collected from the experiment. And as you can see, that's only for data light because we only focus on X and Y acceleration for each accelerometer that we attach on each member. And as you notice, is there no Z direction because as we study and research, in the 3-dimension acceleration will be less than 2-dimension acceleration. That's why we don't include it in our raw data. And another condition when we do experiment is the proportional to our model, arm and leg. So as you can see, the link A and link B is proportional to the lower arm and upper arm of our model. And the data, the result that we get from the full arm swing down for the motion for both instrument and the human test, for the instrument, average maximum acceleration with 71.35 meter per second square compared to our model with 73 meter per second square. And also same as the leg motion, the knee extension, the link C and link D will be proportional to our model thigh and lower leg. And the result out of it that we get is 63.76 meter per second square compared to our model 71 meter per second square. And also this is the data analysis. Every experiment we have to collect 3 times because we want to get the average value out of it to be more accurate. And the reason why we do that, because we don't use the model, is because it give us the consistent data every experiment, which is not represent the best represent the impact movement, the unintentional force. So as you can see right here, the standard deviation for the forearm swing is 0.303, because every trial we never predict how much force you can generate it. So we never predict the outcome for forearm swing that really close and the standard deviation really small. And not only those two motions that we do, we also consider like different conditions, such as the half distance for the forearm swing. And as you can see, is the average maximum acceleration is 54.55 meters per second square, which is closer than the full distance, smaller than the full distance. And also in the different situation that we motion that we did is forearm extension, and the result that we get out from it is 62.48 meters per second square. And the reason like we do all that is because we want to comparing within the closed space with the constraint in a different distance and with different motion, and how much it can be generate the force out of those acceleration. And I will give to Jack to give you a little bit more detail about comparison.
All right, thanks, Min. All right, so as we stated previously, we said that with more freedom of movement as well as less constraints, that we can produce higher acceleration. So we want to see if our instrument is able to replicate this. So on the left, we have two movements. We have the same ones on the right. However, the left is where they're performed at maximum displacement, and on the right, they're performed at only half displacement. So as you can see, the full arm swing at max displacement produces 71.35 meters per second squared. And the same motion, however, at half the displacement produces a smaller acceleration of 54.55. So our instrument is able to replicate this. All right, as part of the NASA requirements, we had to categorize the forces from 5th percentile of women to 95th percentile of men. The masses that we chose are scaled weights of either the arm or the legs. And the forces that we chose are the maximum forces for either movement of the arm and leg, scaled to the 5th percentile and 95th percentile. So how we did these forces was we used the accelerations that our instrument generated, and then using the masses, we generated these forces. So the smallest force is the arm motion for the 5th percentile of women, and the largest is the leg motion for the 95th percentile of men. So we ran some FEA analysis on the back panel of the instrument. This replicates the wallets at the ISS. And we use aluminum 6061 for the testing, as it's a very common material for the ISS. All right, again, similarly fashion, we have it categorized with 5th percentile and 95th percentile. And similarly, the lowest stress generated is for the arm motion for the 5th percentile of women, and then the largest is the leg motion for the 95th percentile of men. And on the right side, the safety factor is 15 across the board. This means that no damage will be occurred onto the structures. So knowing that nothing will happen to the structures, we were curious to see if anything could potentially happen to the astronaut who is imparting the force onto the walls. So we ran an FEA again, this time on either the forearm or the lower leg, depending on the configuration. And we received we used ABS plastic, which has similar density to bone. So once we ran it, we found a minimum safety factor of 0.03. This means that the material would fail, or in real life, that the astronaut's bone could potentially break or fracture. This doesn't take into account our body's mechanics of dispelling energies and forces, such as our general structure, our muscles, tissues, and the bone structure itself. All right, some other applications for this instrument. Basically, we can use it to test any environment that's similar to the ISS. So an open structure with limited constraints, such as subway cars, train cars, buses, or even submarines. However, the main other application would be for studies used in high schools or universities to test for structural design testing, since our instrument is able to generate accelerations or forces onto stationary structures. All right, briefly, economic feasibility. So as you can see, the cost of one is $822, and if you scale that 1 per 1,000 units, it's about $434. So with the small standard deviation, as well as the scalability from being lowest from 5th percentile of women, the force tolerances to 95th percentile of men being the highest, we conclude that our instrument is able to accurately replicate human motion. We'd like to give special thanks to our NASA mentor, Dr. James Smith, professor from UT Tyler main campus, Dr. Shifeng Chu, as well as the computer scientist, Mr. Chingo, and physical therapist, Miss Lisa Swift. Thank you. I'd like to open the floor for some questions.
Hey,
You said that the leg and the arm are proportional. What is that constant of proportionality? How did you determine that?
We are measure the leg of our model, and then we are scaled down like 1/5, so we can cut out piece in the instrument.
any other question?
You move from acceleration to force. So what mass did you use in the
So back. This one?
yes?
All right. So the masses. So.
When you say arm, is it only the
Full arm.
full arm?
Yeah, full arm and then full leg.
And that number came from
It's studies. So they took over like 10,000
good.
measurements.
So, okay, that's what I was wondering
Okay.
because there's a person taller than another.
Of course,
person
yeah.
that
It's an
maybe
average.
as a same for the legs.
Yes, sir.
Okay.
The tray slides back and forth. How did you get the tray to slide at the same acceleration every time? Was there?
It's spring.
It's a spring. We use a spring to attach
Spring
between
loaded on the
the
bottom.
body and the arm.
So at the bottom of the model, we attach a spring to be simulate the impact movement, like moving forward. So that's why we got the data from.
And to keep consistency, we measured the distance every time before we released it.
Any other question?
One question.
Thing number 7.